For part B, we will find work done by force of friction for the round trip, when the block starts at 0, moves to point B, and then comes back to point 0. Force of friction is a difficult, complicated force. First of all, we understand that magnitude of force of friction, it's kinetic friction. So the magnitude of force of friction will be mu n. We need to find n, and most importantly, we need to find the direction of force of friction. So what is the direction of force of friction? Now we need two free body diagrams, because direction of force of friction will be different on the way down and on the way up. Let's draw our free body diagram. What are the forces? There is force of gravity that is vertically down. Force of gravity mg, vertically down. There is normal force perpendicular to the inclined plane. And if the block moves down, then force of friction will be up. It opposes the motion. Force of friction. Okay, now I raised the formula for work. Let's write it here. Work done by any force will be integral fx dx from x1, y1, from point R1 to x2, y2, plus integral fy dy from x1, y1 to x2, y2. I need to choose coordinate system. So what will be my coordinate system? I will choose coordinates, the same coordinate system as we used in part A for the first case when I had my x down. This is my origin. X is along inclined plane. This is my x, and y is perpendicular. Again, remember that the result for work does not depend on your choice of coordinate system. Okay, force of friction is along x. So what is F sub x? Work done by force of friction on the way down. That's important, down. We work with this free body diagram. The projection of friction is negative because x is down, friction is up. I put minus mu n as F sub x. F sub y for friction in my coordinate system is 0. So it was a smart choice of coordinate system. Dx, and what are the limits? I start at 0 and I move to point B. Now I'm ready to take this integral, except one minor thing. So now I need to figure out what is n, what is normal force. And when I look at my free body diagram, I immediately realize that I forgot one more force that the man exerts on this box. So this force is, let's call it P, force exerted by the man. To find n, I will use projection of second law in y. So what is F net F sub y? It is normal force minus mg cosine theta. And this is equal to 0. The box is not jumping perpendicular to y. Ay is 0. So I know normal force, which is mg cosine theta. Great. It is constant. This force is constant. So I can take it out, mu n, I take it out of integral. It is minus mu. N is mg cosine theta, x, and x is b minus 0. This gives me b. So this is work done by force of friction on the way down. Now let's find work done by friction on the way up. I will use different color. Work done by friction on the way up. Let's draw the free body diagram first. Gravity, no changes, of course. Normal force perpendicular to the inclined plane. Force P still in the same direction. What's different on the way up? When the box is moving up, force of friction opposes the motion and it is down. This is force of friction. The magnitude of force of friction is the same, but projection will have different sign. So this is work done by friction on the way up inclined, the inclined plane. Where do we start? We start at point B. We end up at point 0. I need F sub x. Force of friction is down. My x, my choice of x, is down inclined plane. So the projection of force of friction on x is positive. That's why I put plus mu n dx. N, we already found n, great. So it is mu, n is mg cosine theta, x. And I plug in the limits for x. It is 0 minus b. And work done by friction on the way up is minus mu mg cosine theta b. So what is work done by friction for the round trip? I think I have space to write it here. There. Where? Here. Work done by friction when the block moves from 0 to B and then back to 0 is minus 2 mu mg b cosine theta. We answered the question B. What is work done by friction? I have one more part of this problem, one more question for you. And the last question that we need to answer is, what is work done by force P, done by the man? So part C, that's what we need to answer now. And that's not a good idea to use the same color. Let me switch colors for you to see that it is a new chapter, not chapter, new endeavor. C, part C. We need to find work done by the man for the round trip again, from 0 to P, B, and then back to 0. So what is it? Well, imagine this. So you're pushing on this box, and despite your effort, it is sliding down. And then you manage to push it back. Obviously, force that you apply, we call it force P, force applied by the man, is not constant. You cannot just take it out of integral. That would be nice. No, you cannot do it, because as the block travels down and up, force P is changing. It is changing with x. We don't know how it changes. So we cannot just take this out and, yeah, great, we know the answer. We cannot do that. But what we can do, we can use the work energy theorem. Look at this. They told us something about forces, but they also told us that the block starts from rest, slides down from the top, and then gets pushed to the where it is again at rest. So we know something about initial and final velocities. We can use work energy theorem that tells us that work done by the net force is change in kinetic energy. Final kinetic energy minus initial kinetic energy. What is the initial kinetic energy? The box starts from rest. It is 0. What is final kinetic energy in this case? it stops there, so it's again 0. All I need to do, I need to find work done by net force, which in this case is work done by gravity plus work done by normal force plus work done by friction plus work done by the man. And all this is 0 because the change of kinetic energy in this case is 0. So what is work done by gravity for the round trip? It is 0. What is work done by the normal force for the round trip? It is 0 because work done by normal force is 0. Normal force is perpendicular to the displacement. That's why work done by normal force is 0. Then work done by friction. We have work done by friction for the round trip is twice mu mg b cosine theta plus work done by the man, and this is equal to 0. Look at this, how powerful work energy theorem is. It gives us work done by this man without even knowing how force is changing. So it will be twice work done, it will be twice mu mg b cosine theta. It will be equal to work done by friction because all other will give you 0 gravity and normal force. We solved the problem. Work done by the man is equal to this expression, and everything that I have on the right are given numbers. We know mass, we know mu, we know b, and we know theta. Problem solved.